In this video, we want to take a look at actually doing a couple examples of comparing two population means. In the first video in this section, we talked about the general topic and introduced the idea of comparing two means using a couple different sampling techniques. But hopefully you found that the tools that we're using, the confidence intervals and the test hypothesis, are pretty similar to things we've done before. Not a lot of surprises or changes from the techniques we've worked with before. I guess the confidence interval interpretation is a little bit different, but by and large, it's pretty much the same. And if I'd have stopped with that, that would have been great. Could have looked at some examples. However, the second video, I opened a can of worms. We talked about having to estimate variances, and most of the time after I have that conversation, students are left, their heads are spinning a little bit, and they're thinking, what the heck is going on? So I want to take our time here and look at a couple different examples where we actually go through and estimate the variances and talk about that process. And hopefully what you're going to find is it takes longer to talk about it and explain it than it actually does to use it. And so with that, let me go back to the example I started that whole mess with, where we're comparing two independent random samples. And in this particular example, we want to test to determine if mu1 is less than mu2. Now, it's a pretty easy way of stating it because our first step is to set up the test hypothesis. We'll come back in a second. We'll talk about the confidence interval, but setting up the test hypothesis, you need to be able to identify the null and the alternative, and it's right there. We want to show that mu1 minus mu2 is less than 0. The null is it's equal to 0. We always have an equal to component in the null. And I can move on from here, but I want to take a minute just to talk about this test. Typically, what folks are going to be interested in is trying to determine if one mean is bigger than the other. Now, the way I've written it here, I'm checking to see if the second mean exceeds the first mean. And I can say that one of two ways. Think about my age and your age. There's a really good chance I'm older than you. I've been doing this a while. You're probably a more typically aged student, and I know there might be someone in a class that's not true, but by and large, I'm older than you. Now, the other way of saying exactly the same thing is you're younger than me. Right? They're equivalent statements. You can take a look at it from either perspective. The reason I'm bringing this up is because I could ask you to do a test here to see if the first mean is lower than the second mean. And when you hear that word lower than, you naturally think less than. And you say, oh, that's a less than test. Great, no problem. But what if I told you about it or asked you to do it the other way around? Test to determine if the second mean exceeds the first mean. And when you see and hear the word exceeds, you're probably thinking greater than, greater than, greater than. And that's where you have to be a little careful when we're comparing means, when we're comparing proportions. Actually, when we're comparing anything, be careful. You have to consider the order. And so if instead of saying it in the way I did here in part A, what if I said test to determine if the second mean exceeds the first mean? And we're talking about population means here. You would do the same thing. It would be a less than test. Specifying the alternative is a little tricky when we're doing one-tailed tests because the words that we've seen so far, words like exceeds, is greater than, is below, is less than, may not end up with the obvious choice. Test to determine if the second mean is less than the first mean. That's not a less than test. That's a greater than test. Mu1 minus mu2 is greater than 0 in that case. And so you have to be careful with the wording. It's subtle, but it makes all the difference in the world. Identifying the alternative is what drives me to this printout here. And this printout, as we talked about before, this is just the sample information. It's taking this information here in these two samples and saying, this is what you gave me. This is the data you entered. This part here shows up because that's the test I asked for. This comes first, and that generates or drives the printout over here. Now, the part that we interpret is the part down here. Specifically, it's this top part, these two right here. This is the part that we actually interpret, but sometimes this guy comes into play down here. All right, so the test statistic and p-value, we're going to get them from here and here. But you can see there's two rows. And actually, if you watch that last video, I talked about there being three methods or three options. The first option is really easy. The first option is if we take large samples, automatically go and grab the unequal information. So take the test statistic, take the p-value, and run. And that works great if our sample sizes are large. Now the criteria we're using here, 30 or more. Both N1 and N2 have to be 30 or more. They're not in this case. A more general cautionary statement here, 30 or more is not always the sample size criteria you should use. It is when we're working with means, but we're not always going to be working with means. We might be doing some regression. We might be doing some proportion work, some categorical data analysis. There are all sorts of sample size criteria. A general rule of thumb is, if I ask you, is the sample size large, before you say yes or no, consider what you should be looking at for the sample size. What's the criteria you should be using? In this case, they both need to be 30 or more. We have small samples, so we can't automatically grab the unequal row. Gosh, that's easy when we can. In a lot of situations, it's not difficult to get large samples. And so a lot of times, all we got to do is grab the unequal row. I know a lot of people teach this class. I don't even have this conversation with you. They just say, we'll make sure they take large samples. We'll be good with it. I want you to think through it, because really it's not that hard of a process. If you have small samples, before we know what to do, before we know which row to go to, we need some indicator. We need something to point the way. We need something to tell us whether these variances are the same or not. And the place that we get it is we come down here, homogeneity of variances. What the heck does that mean? Equality. Think about equal. Equal. Homogeneity. Equality of variances. There's a test being conducted here. The null hypothesis says the variances are equal. And we need some way of trying to figure out, is that true? What we're going to look at is this p-value. And the question, there's some wording that I'm going to start using, is that a rejectable p-value? Huh? What the heck did he just say? Is p low? What I've tried to present to you, the test hypothesis topic, when p is low, you can reject the null hypothesis. The null is saying that the variances are equal. If this is a small number, if this p-value is low, we can say that the variances aren't equal. We're going to reject they're equal. We're going to say they're unequal and use the unequal row. Is this rejectable? Is p low? Compare it to alpha. Now, in this test, I told you to use an alpha of 0.10, but that refers to up here. In another example, I might say use an alpha 0.01 or 0.05. All those are acceptable values for alpha. When you're doing this variance test down here, we're going to make alpha as big as it can be. I always want you using 0.10 when you're doing this variance test. Doesn't really matter in this case, though, does it? Is this p low? It doesn't matter if you're using 0.01 or 0.05 or even 0.1. P is not low. P is high. We fail to reject. We can't say that the variances are unequal. We're going to use the equal row. And so that's the row of information we're going to grab. Now, a lot of you guys are a step ahead of me. You're saying, well, in this case, it doesn't matter. Look, the test statistics the same. The p-values, they're the same. Look, even the endpoints on the confidence intervals are the same. The numbers are different. You can see there's a slight difference in the two rows here. This p-value might be 0.000002, and this one might be 0.000018. But for our purposes, this p-value is low. And so we start here with small samples. We start here, and this p-value says go and grab the equal to information. Go and get the information from the equal row. And so the test statistic is going to be this top one, the negative 5.12. This guy here, let me put a box around it so we're making sure. The p-value is this one right here. In a second, we're going to talk about the confidence interval points, and we're going to grab that top row. We're going to grab the equal row. We're going to ignore the unequal in this case because of this p-value right here. So I'm marking this thing up pretty bad, but interpret a p-value for me. At alpha equal 0.10, this p is low. We can reject. There is sufficient evidence to indicate the mean for population 1 is less than the mean for population 2. Another way of saying it, an alternative that works just as well, there is sufficient evidence to indicate the mean for population 2 exceeds the mean for population 1. If 1 is less than 2, then 2 is bigger than 1. You can say it either way, it doesn't matter. Interpret the confidence interval endpoints. Now when you look at the confidence interval, again, we're going to go to the equal row. I see this. I see a negative lower endpoint and negative upper endpoint. What's that mean? Again, I can say it either way. We're 98% confident the mean of population 2 exceeds the mean of population 1, or I can say it the other way. The mean of population 1 is less than the mean of population 2. I wanted to show you both ways, so I said it one way here. I said it an opposite way there. We have this extra step. When you take small sample sizes, you have this step here you got to go through. Large sample sizes, we immediately go to the unequal row. It's a piece of cake. So we take that whole variance question out of the equation simply by taking large samples. And so that's how we analyze these results. So we're going to go and take a look at another example on the next slide. All right, so in this one, we have marketing strategists would like to predict consumer response to new products and their accompanying schemes. Consequently, studies that examine the difference between buyers and non-buyers of a product are of interest. A recent study is interested in determining the average age of buyers and non-buyers of Crest toothpaste, or if the average age differs. The printout appears below. Years ago, I think going back in the 1970s, there were some studies that were done looking at the mean household income of buyers and non-buyers of Crest toothpaste, and also the mean household size, how many kids and how many people were in a family. And it was determined that differences existed. Actually, it turned out that the folks who bought Crest toothpaste tended to, on average, make more money and on average have larger families. So interesting results. This one's saying, let's take a look at the ages of purchasers and non-purchasers. And you can see the groupings up here. We have N's and we have P's. N's for non-purchasers, P's for purchasers. And you can also see, I wanted to do another example where we had small sample sizes. Make it tough for you. The tougher I can make it in the videos and the examples we do, the easier other things will be by comparison. If we had large samples, we'd just grab the unequal row and run with it. But in this case, we'll get that extra step again. So here's what I want you to do for me. I want you to do a test hypothesis. Do the data provide sufficient evidence to conclude there is a difference? Notice the printout I gave you. I gave you a two-tailed printout. I'm asking for a two-tailed test. So that should be pretty straightforward. And then interpret the 90% confidence interval for the difference between the mean age of purchasers and non-purchasers. And of course, I'm going to finish up with, I shouldn't say of course, I'm going to finish up with the assumptions. What assumptions? And I want you to think about them in the words of the problem. And so let's go ahead and take a look at how we do this. So first, test. Let's do the test hypothesis. Test to determine if there is a difference. What's the null and the alternative? What would you write for the null and the alternative? This is what I have. The null is going to say the means are the same. If you're testing for a difference, we're going to do a two-tailed test. That's what drove this printout. The difference between the means. I'll write it this way, mu1 minus mu2. But the fact that I was doing a two-tailed test, when I went to the computer, I said, all right, that's the printout I want. I actually had to specify the not equal to. Again, in another video, I'll show you how to generate the printouts for comparing two population means. Now, the question is for the test statistic and the p-value, and you can see again, the test statistics are going to be the same in this case. In fact, when you have equal sample sizes, they will be the same. But the p-values are a little different. Which one's the appropriate one to use? Should I use the equal row or the unequal row? And again, with my small sample sizes, because one or more of those is less than 30, I have to think small. I got to come down here, and I got to take a look at that. And when I look at that p-value, it's close, but p is low. It's less than 0.10. What does that mean? When p is low, I can reject that the variances are homogeneity. I can reject that the variances are equal. I don't think they're equal, so guess which row we're going to get rid of? I don't think the variances are equal, so I'm going to get rid of this information here. So this low p-value points to the unequal row. And so when we go to grab the test statistic, when we go to grab the p-value, we're going to grab them right off of that, and that p-value is not right there, and that test statistic's not right. I'll have to change that on your notes. Actually, you're writing this in. What should the values be? T is equal to, I just copied and pasted from that last problem, and I didn't change them. 1.96, and the p-value is 0.0585. It's funny because I grabbed that and I grabbed the confidence interval and I copied and pasted, but I changed the other one. There we go. So that's what you should have in your notes. The test statistics right here, the p-value is right there. And now interpret that for me. Well, at alpha equal what? Let's make it 0.06. We reject H naught when p is low. At 0.06, we reject. What would you do at 0.05? You'd fail to reject. So we're rejecting. I'll say at 0.06 we reject. There is sufficient evidence to indicate that the mean age of the first group, the non-purchasers, differs from the mean age of the second group, the purchasers. If you were testing at 0.05, what would you change? Well, in here you'd say rather than rejecting, we would fail to reject, and here you would say there is insufficient evidence. So it depends what alpha you're going to test at. Am I going to mix and match alphas? And sure, yeah, it's what I do. You got to keep up. You got to know how to use this stuff. You should know first to use the unequal row because of that folded F p-value. Once you get the 0.0585 off the printout, you should know to compare alpha to that. If alpha is 0.06 or 0.07 or 0.08 or 0.09 or 0.10, p is low, reject. There's sufficient evidence to indicate that the first mean differs from the second mean. How would you interpret the 90% confidence interval? There it is. You can see I copied and pasted, but then I changed that. The 1.0068 to 13.793. The positive, right? What are you going to say? You're going to say the mean of the first group is what? Bigger than the mean of the second group. That's how you interpret an interval with two positive endpoints. We're going to say we are 90% confident that the mean age of the first group, the non-purchasers, exceeds the mean age of all purchasers. We're going to say mu n is greater than mu p. Could we flip that around and say mu p is less than mu n? Of course we could. The mean age of all purchasers is less than the mean age of all non-purchasers. And then the last question I'll take a look at, what are the assumptions we need? And I want you to kind of go through the four things we've talked about. We've talked about random. Do we need a random piece here? Yeah, we always need a random piece. The two samples need to be randomly selected from their populations. This is an independent technique too. We need random and independent samples. Okay, let's see how I did that. We need random and independent samples. Because of small sample sizes, we need both populations to be approximately normal. Now, what does that mean? We need, what are we working with here? We need the ages. That's what we're actually sampling. We're asking people how old they are. Do you buy Crest? Oh, you're a non-purchaser. How old are you? Oh, you over there, you buy Crest? How old are you? So the ages of all purchasers and the ages of all non-purchasers both need to be approximately normally distributed. And typically you hear me say the population of X's, the data. What are you actually working with here? We're comparing ages, ages of purchasers and ages of non-purchasers. Where's the word all come from? Because we're talking about populations, the ages of all purchasers in the population. People need to be approximately normal, the ages of all non-purchasers. Do we need equal? So we have random. There's one of our words there. We have independent. There's another word. Approximately normal. That's our third kind of idea. Do we need equal variances? Well, what did this say? This said we don't think the variances are equal, and so we don't want to make that assumption. In the last problem, where we used the equal row, we would need to assume that the population variances were equal there as well. I didn't do the assumptions in the last problem because it really wasn't a words type of problem. It was just kind of a nuts and bolts. Here's how we do it type of an example. In the last one, we would have needed random. We would have needed independent. We needed approximately normal. And in the last example, we would have needed equal variances as well. Here, because we're using the unequal row, we do not need that assumption. And so that's how we take a look at it. Confidence intervals and tests of hypothesis. Hopefully that makes sense. Sorry for the snafu here in my notes. Bad copy and paste, and I didn't have a good alpha here. But other than that, hopefully it makes sense to you. If it doesn't, you know how to get hold of us. You got some way of checking it now. So go take a look at the competency check. Make sure this stuff makes sense to you. Do some homework, do some practice, and ask questions when you get them. So long.